I'm a third-year PhD student at the University of Melbourne. We are living in exciting times, JWST, the COVID. So this is my first in-person conference talk. So these are the names of the people I bother the most in my PhD. I officially am a PhD student with Stuart and Brad, but I always send my plots to everyone mentioned here, especially Yushang. So today I'll be talking to you about simulating the epoch of reionization. So you have the first stars and the first galaxies, which form the ionizing UV photons, and they will basically knock out the electrons from the hydrogen atom. So in the early universe, somewhere between the redshifts of 30 and 6, you have the phase change of H1 to H2. And here you can see these bubble structures forming around the white dots, which are the galaxies, and the red color is the cosmic H1 gas. So I saw this slide from Brad. So you have the so the main thing I want you to notice from this one is this term here, the spin temperature term. So that's a Ts minus T gamma. The T gamma is a background light, and we are almost always take the gamma to be the CMB photons. So you are also observing the spin temperature against the CMB light, and the spin temperature is a proxy for the hyperfine levels of the H1. Moving on, so if you ask someone who does simulations, this is the main issue which they have. So you have these H2 bubbles, and the typical size for these H2 bubbles are of the order of 15 or something megaparsec scales. But these structures are formed by small galaxies. I mean, small in the terms of these scales, galaxies, and which are the source of these photons. And when you go into the galaxies, you know that the actual photons are actually from the stars and galaxies. So if you really want to simulate these things, you actually should start from the level of the stars, which is not possible. So what we do is something called a semi-analytical model, or SAM. The SAM which we use is called Meraxes, and Meraxes is special in the sense that we got a modified version of 21 centimeter fast inbuilt as well. Now 21 centimeter fast is something called a semi-numerical code. It's fairly fast enough, but the main drawback of 21 centimeter fast is that you don't have a proper galaxy source population in the code. So in Meraxes, you will evolve the galaxy and the galaxy properties. And the 21 centimeter fast part of Meraxes will actually do the EOR calculations for you. So what did we do? So we wanted to explore a few phenomena. So we want to explore the impact of this mass solution on the EOR signals, as well as the impact of the X-rays on the EOR signals, as well as something called the non-Gaussianity of the EOR field from the cosmic variance. So how did we do this? For exploring this mass solution impact, we took the Genesis, the largest Genesis simulation we have at the moment. It's a 210/h megaparsec box. So this mass solution of the Genesis box is somewhere over here, which is good. But what we did next is we improved this mass solution of the Genesis, and we are now introducing a new simulation called Genesis Plus. And that's a Monte Carlo augmented simulation, and this Genesis Plus has a mass resolution which is the same as the atomic cooling limit at redshift 20. Now this simulation actually has all the dark matter halos, and consequently all the possible galaxies which exist down from redshift 20. Now, yeah, so if you want to know more about this one, you should go look at this paper, or I'll be happy to explain offline. And when we run Meraxes on this one, these are the neutral hydrogen fields. If you look at the top panel, you can see the Genesis Plus simulation, and the bottom panel is the Genesis one. You can see more structures in the Genesis Plus, which is because of these smaller halos. Now, what I can do is we can take a difference of this one, and now we can see this small structures. If you look at the EOR signals, so the main two signals which you focus on are the mean signal as well as 21 centimeter power spectra. Yep. And as you can see, the fact that you actually have these small dark matter halos does have an observable impact on your EOR signals. Moving on, where we are exploring the impact of the X-rays. The reason we want to do this one, the main impact of X-rays is that they actually heat up the gas. So they basically control the spin temperature of the gas. Now, this is just a technical detail about how the X-rays actually implemented inside the code. So the input to Marax is something called a soft band luminosity per star formation rate. So we now introduce two more simulations, which is the low X and the high X. What you need to notice from this one is not the exact value of these X-rays, but the low X obviously has less number of X-ray photons in the early universe, and the high X has more number of X-ray photons in the early universe. Now, if you look at these your signals from the where I'm varying the X-rays, you can see that it actually makes sense. For example, if you look at the Genesis plus high X, where I have more number of X-ray photons, the gas, the spin temperature will actually be much higher in this case, which is something you notice here. So in the same manner, you actually have an impact on the 21 centimeter morphology, which is reflected in the 21 centimeter PS as well. Now, in the last part, we wanted to explore this cosmic variance effect. So what we did is we took the fiducial Genesis plus simulation and we chopped them up into smaller subvolumes. And if you look at your history in the fiducial Genesis plus as well as subvolume, you see a spread, which is something you expect, obviously. This is just a cosmic variance effect. Now, in the same manner, if you look at the power spectrum from this, the whole box as well as subvolumes, you actually see a spread. And you see the spread more in the low K values or the large scales. This is also something you expect. Now, you might know that if you look at a normal random field, you can look at the covariance matrix of the field. And the covariance matrix is given by this expression where V is the volume, K is the special frequency, and the P of K is your power spectrum. And the T of Ki, Kj is a trispectrum, which is now, it is essentially the Fourier transform of the 4-point correlation function. Now, mathematically, you can show that if your field is actually Gaussian, you only need a 2-point correlation function. Every higher order correlation functions can be expressed in terms of 2-point correlation function, which means the entire information is encoded in the power spectrum. So what that means is that if I'm ignoring this second term, I'm assuming that the EOR field is basically Gaussian in nature. And when you do that, this matrix actually becomes a diagonal matrix. And what you can do is so these diagonal elements will now be the variance of your each power for these K modes essentially. Now, so this is going to be the expected cosmic variance error for a purely Gaussian field. Now, since I have this large subvolume, large volume, and a large number of subvolumes, I can actually measure this variance now. So what I have done here is I have applied this formula, and I have also taken a standard deviation of this across the subvolumes. Now, if I take a ratio, if the field is actually Gaussian, it will be exactly 1. And as I'm sure most of you are aware, you will never get that value. So what do you see from this one? So it's essentially the sigma measured across the subvolumes divided by the sigma which you expect. And what you see from this one is that there is non-Gaussianity even at high redshift for small scales or large scale, for example, here. And for large scales, the large scales are more Gaussian in nature, especially at high redshifts. And that's the main things I've done in the last 2 years. And Just leave it here. Yeah, thanks.